especially to Elizabeth's family for being here. I did not have the fortune to meet Elizabeth, but from all I've heard about her, she was a brilliant mathematician and a wonderful human. And so it is a great honor for me to be here, invited to give the inaugural lecture in her memory. So thank you for joining us, and thank you to those who are joining us online. Hello, online people. I'd just like to tell the online people that there will be a little activity later on. If you have a piece of rectangular paper and a pen, then you will be able to join in. I'm going to talk about my first book, How to Bake Pie, which is about math and food. I love math. I also love food. And it makes me sad that so many people seem to love food so much more than they love math. And so I've decided to try and share my love of math as widely as possible via my love of food. And that's what I'm going to talk about today. But first of all, I need to say what I mean by math, because unfortunately part of what I think is the problem is that many people have a very, very narrow view of what math is. Math is not just about numbers and equations and getting the right answer. I say that math is about much more than that, including some of my favorite things, such as Bach, juggling, hair, factors of 30, okay, well that's fairly mathematical, cake, and custard. So how is it that math is part of all of these things? Well, what is math? I say that math is the study of how things work. But it's not the study of how any old things work. It's the study of how logical things work. And it's not any old study of how logical things work. It's the logical study of how logical things work. But the trouble with that is that nothing actually is logical. I'm not logical, you're not logical, the computer's not logical, this projector definitely turned out not to be logical. Nothing is actually logical, and so in order to study anything logically, we have to forget some of the pesky details that get in the way of things behaving logically. And that takes us from the real world of concrete things into the abstract world of ideas, where things really do behave logically. And that's what math is, and that's where math lives. But in that move, you end up feeling like maybe you don't have your feet on the ground anymore, because you kind of don't. And some people don't like going into the abstract world, because in that world, you can't win arguments by yelling. I could win arguments by yelling, because I'm quite loud, but I prefer not doing that. So I like understanding things in the abstract world. But because it's difficult to see and touch things in the abstract world, I like relating them back to things that we all know and have experience of more, which is why I talk about math being in all of these other things. So first of all, a piece of Bach. Bach is one of my favorite composers, and it does have a lot of math in it for many reasons, most of which I won't talk about, because I could probably talk about that for an entire lecture course all by itself. But Bach wrote a set of pieces called the Well-Tempered Clavier, because they had just used some math, as it turns out, to figure out how to tune keyboards better. And before that, you couldn't really write music in every key. But then they figured out how you could write music in every key. So Bach got really excited and wrote a piece in every key. There's 12 notes on the piano, so that makes 12 keys, but there's also major and minor, and he did both, so that makes 24. Then he got really excited and did the whole thing again, so he did 48. And this is from the second book. It's the Prelude in G minor from book 2. So I will start by playing it for you. each other. And in theory, you could get individual people to sing each line of music separately. And what you often do when you're studying a piece of music in polyphony is you isolate each line of music first and follow it around. And so in this one, the first person to come in is the bottom note, ba, and then someone goes, doo 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 doo, and then someone else goes, ba da 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 doo 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 doo. So when I was first studying this piece of music, I got really confused. So I decided to draw a diagram of the lines of music winding their way around each other. And the picture came out like this. So the top line, the black line, is the soprano, but the thing is that the soprano winds its way down and ends up as a tenor, whereas the green alto line ends up as the bass. The blue tenor ends up as a soprano, and the red bass line ends up as an alto. And so I understood why I didn't understand. And understanding why you don't understand is the first step to understanding anything, right? So I understood the reason I got confused was because these lines of music cross over each other and they don't come back again, which is quite unusual in polyphony. It would be very difficult to get 4 people to sing this because all the voices end up as different voices. I do know one person who can sing soprano, alto, tenor, and bass, but that's quite unusual, and that was only one person. So the thing is that when I drew this diagram, I was a master's student, and I didn't know that I was doing math when I did that. The first paper that my advisor gave me to read when I started my PhD had pictures like this in it. It was Joyal and Street's paper about tensor categories, graded tensor categories. But I looked at the pictures in that paper, and I thought, crikey, that's like that picture of a bar prelude I drew last year. And so sometimes, it turns out you're doing math even when you don't realize that you're doing math. And the thing about this diagram is you don't have to know it's there in order to listen to the piece of music. You don't even have to know it's there to play the piece of music and enjoy it. But I found that looking for that structure and finding it helps me play the piece of music better. And that's what I think about the math that's inside stuff all around us. You don't have to know it's there. You can, in fact, get on perfectly well with your life if you don't know it's there. It's just that I think you can get on better if you do know it's there. And just like, well, when we use buildings, we don't have to understand how they're built. We don't have to know where the structural walls are in a building to use a building. But it's a good thing that somebody knows where the structural walls are. So this is in fact related to juggling. Now I used to say I'm terrible at juggling, and then someone pointed out to me that that's like people who say they're terrible at math, and that it's better to say I'm not that great at juggling yet, but I'm getting better. I'm still not good enough to particularly want to do it in public, so I'm wondering if there's someone here who could do a juggling demonstration. Can anyone save me from having to do a juggling demonstration? Please? Someone?
Balls or pins?
Balls. Wonderful!
Well, Peter.
Thank you very much. What's your name?
Peter.
Peter, thank you. Just normal 3-ball juggling. Across the stage that way. Could you start at that end? Would you mind starting at that end and walking this way? I invite you to do that again. Now, everyone imagine that the balls are actually tracing paths through the air, and that we can maybe take a long exposure photo. What paths do you think that is going to make? What pattern is that going to make through the air? Thank you very much. Big round of applause. So I did make a long exposure photo using some illuminated juggling balls. This wasn't me. The one I did was really wonky. This was an 8-year-old boy at a school I was working at. But here is one I made digitally. So if I start at this end, you can maybe imagine what happens is I'm going to start with the green and the blue balls in my left hand, and I'm going to do a slow motion, hilarious juggling demonstration. So the blue ball goes this way, right? And while it's going, I throw the red one underneath it. So while the red one is going that way, the green one then comes underneath that one. And while the green one is going that way, the blue one is going that way. And so it makes this pattern. And if I turn it on its side, you see it's the same as the braid in my hair. Because that is how you make braids. And then you can say, oh, actually, it's related to this bark braid. This is also things making a path through the air. Now, I once tried braiding my hair like the bark braid, but it didn't go very well. Because maybe you can see that nothing would really stay put. Like this green strand is just floating around doing nothing. And so is the black one. The red and the blue ones are interlocking, but you could just kind of pull this green one down and pull that black one up. In order to get it to stay, you would have to use an extra band here, probably, another one here, maybe another one there. Whereas the whole point about the ordinary braid is that you can keep all your hair tied together with only one band. So if I take this band out and then pretend I'm in a shampoo commercial, it was one of my ambitions when I was little. Then you can see that it is, in fact, only held together by one band. But mathematicians study these. They're called braids because they're like braids. And then we study things like, well, which braids are the same as the others? If you count it as the same, if you keep the ends fixed, but you can pull the other ones around, which ones can you make into other ones without having to break them or to put strands through each other? And they started doing this just sort of for fun, because it was fun. But then it turned out to be useful as well, because it may be related to things like perhaps early diagnosis of Alzheimer's disease, which might be to do with brain cells getting knotted up in a mutation. And then we maybe need to tell which ones are knotted in genuinely different ways, and not just that we're looking at them from a different angle. And for that, you can't just stick your finger into someone's brain and pull out a cell and wave it around to see if it's the same. So you need abstract techniques for studying it, and that's where some of the math comes in. Now, because I couldn't braid my hair like this, I decided to make it into a pie instead. So this is my Bach pie. It's a banana and chocolate pie. Get it? Bach. Anyway, so moving on to something that is more obviously mathematical, the factors of 30. Well, maybe we can remember what the factors of 30 are. The numbers that go into 30 are 1 and 2. Very good. And also 3, 5, 6, 10, 15, and 30. Amazing. It's very boring. It's not at all interesting. It's a bunch of numbers floating around in a straight line. We often stuff our thoughts into a one-dimensional straight line. I say it's because we live in a three-dimensional world. So we write it on two-dimensional pieces of paper in one-dimensional straight lines. And we stuff all our thoughts into that straight line. Maybe they don't want to be in a one-dimensional straight line. Maybe they have natural geometry in higher dimensions. Like why I say I don't tidy the papers on my desk. Because they have natural geometry in higher dimensions. They don't want to go into a one-dimensional straight line. So let's find the natural geometry of this situation by looking at which numbers are also factors of each other and drawing a kind of family tree. So 30 is at the top, like a sort of great-grandparent. And then 6, 10, and 15 are the direct descendants of 30 with nothing in between. 5 is a direct descendant of 10 and 15. And we don't need to draw a line from 30 to 5 because it's like great-grandparent generations. You don't have to draw those in a family tree because you can deduce them from the successive parent-child generations. 2 is a direct descendant of 6 and 10. 3 goes into 6 and 15, and 1 goes into 2, 3, and 5. So now we see it's the corners of a cube, much more exciting than a bunch of numbers in a straight line. And if you're thinking like a mathematician at this point, you can go, why did that happen? Does every number make a cube? What other shapes can we make? What happens if we do other numbers? But for today, what I'm going to do is take this cube really seriously as a cube. And I'm going to imagine I'm wrapping it up with ribbon like it's a gift. And so what I'm going to do is I'm going to follow the pattern of the faces. So my ribbon is going to cross over there, and now the red strand will continue down this way, and the blue strand will continue that way. Now I need another ribbon over here, so I'll make that one green. But on this side, I'm going to start the ribbon in the same places, but follow this part of the cube. And so it's going to make this pattern. And now you can stare at it and go, actually, those two aren't really different according to what we just said about braids, because if I kind of pull this green strand up and shuffle that red and blue strand down again, hope you can see that this braid will become that braid. And this is a really fundamental fact in the study of braids, because one thing that was done in the study of braids is trying to figure out which moves are the fundamental basic moves that will generate all the other ones. That's something that we do a lot in abstract math. There's a very complicated situation, so we have to try and understand it via simple basic building blocks. And of all the ways that you can wave pieces of string around, you can break it down into a basic 3. And this is the third one. It's otherwise known as the third Reidemeister move, because mathematicians love giving things fancy names to make ourselves feel clever. But it turns out that the square-shaped one comes from a different part of mathematics in higher dimensional algebra, and there it's called the Yang-Baxter equation. And the fact that the Yang-Baxter equation is related to the third Reidemeister move is really the fact that when you wrap presents up with ribbon, you get the same braid. And then so I looked at that and I thought to myself, wait, wonder what if I did that with my Bach braid? So what I'm saying is, if I take my Bach braid, can I reverse engineer a gift that is the exact correct shape to be wrapped up by that braid? So I stared at it for a bit, and I thought, well, it's kind of a third Reidemeister movie thing up there, and another one down there. I think it's a cube. And so I thought, no, I can't. So I can't be a cube. So I made a cube, and I drew on it, and I went, it's a cube. And so I did exactly what I do every time I think I've proved something in math, which first I go, ah! And then 1 second later I go, it's probably wrong. And then 1 second after that I go, I bet everyone in the world knows this apart from me. And so I phoned my friend, the one who can sing soprano, alto, tenor, bass. I said, look, a cube! And he goes, I think it shows that Bach was communing with the spirit of the Platonic solids. I don't think that's what it shows. I don't know what it shows. I don't know if it matters. I don't know if it means anything. I don't know if it's helpful to anything. I just think it's kind of cool. And sometimes when something relates to something else, it's just kind of cool. Isn't that enough? Why does everything have to be useful? It's cool. Cool is useful. So is Battenberg cake. I love baking and I love cooking. My favorite thing to make is cake and any kind of dessert. I love making dessert because it has no nutritional value whatsoever. It exists solely for my enjoyment, and I like that. And the Battenberg cake is one of my favorite kinds of cakes. It's a very British sort of cake. It has come over here since the Great British Baking Show has been here, which incidentally is called the Great British Bake Off in Britain, but I understand that was trademarked by Pillsbury, so they couldn't call it that. Anyway, in that show, they often make Battenbergs, and it's something to do with maybe the crest of the Battenbergs. But anyway, the point is that you have two colours of cake, and you definitely don't want the same colour of cake to touch the same colour of cake, because that would be terrible. But this pattern appears in all sorts of places. For example, if we make a little multiplication table of 1 and -1, well, you have 1 times 1, which is 1, usually. Then 1 times -1 is -1. And -1 times 1 is also usually -1. But -1 times -1 is 1. So it's a Battenberg cake. And we can try this with addition of even and odd numbers. So if you add an even number and an even number, you get an even number. If you add an even number and an odd number, you get odd. And if you add an odd number to an odd number, you get even. It's a Battenberg cake. So now I can show you something that you may not have heard of. You might not remember what imaginary numbers are. You might never have known what imaginary numbers are. But imaginary numbers are that thing that happens at school when they say to you, you're not allowed to take the square root of a negative number. And then the next year they go, okay, now we're going to take the square root of a negative number. But anyway, it's a Battenberg cake. So regardless of whether you ever knew that, we can tell that a real number times a real number must be real. And a real number times an imaginary number must be imaginary, but an imaginary number times an imaginary number is real. So these are all Battenberg cakes. In math, they're known as the cyclic group of order 2. Specifically, it's the Cayley table of the cyclic group of order 2, which is a lot of words, and you don't usually study that until you're in some kind of abstract algebra class, maybe. But it's a Battenberg cake. I also think that there might be a Battenberg cake of tolerance. So we can get ourselves very hung up, if we're trying to be tolerant people, which I hope we are, about whether that means we have to be tolerant of everyone. Does that mean we have to be tolerant of intolerant people? So I think that actually, well, obviously we should, being tolerant of tolerance counts as tolerance, and that I think that being tolerant of intolerance doesn't mean you're directly being intolerant, but you are enabling intolerance to continue. And so I think that you're contributing to intolerance if you're tolerant of it. Whereas I think that actually we should be intolerant of intolerance, and that counts as part of being tolerant. So I think it's a Battenberg cake. So another place where Battenberg cakes come in is when we do bed flipping. So mattress flipping. Mattress flipping is allegedly what we're supposed to do every season to stop our kind of bottom from pressing into the mattress in the same spot all year. Now, I never do it because I'm much too lazy. But also, if you've got one of those fancy mattresses with a top on it, then you don't want to flip it because then it'll be upside down. But of course, if we were going to flip our mattress, we would definitely write A, B, C, and D on it to make sure we keep track of where we are. So that's why hopefully you've all got a little mattress with A, B, C, and D on it. If you're watching online, you can take any rectangular piece of paper, bless you, and write A and B on the front. So A at the top, and then turn it upside down and write B. And now here's the tricky part. Turn it over sideways and make sure the C is pointing at the same place where the A is, and that the B and D is in the same place. It'll still work if you do it another way, but we'll all get different things and then we'll all get very confused. And so there are 4 things that you can do with your mattress. And we can make a little multiplication table of them as if they were numbers. So the first thing you can do is 0, which is nothing because you're me and you're really lazy. But you can also do, so rotation, I'm going to say that we're always going to start with our head in the A position. Rotation means that we rotate our mattress without turning it over. And then flip means we flip it over. And flop means we flop it over the long way. And so the first thing we can do is we can do nothing and then do nothing again because we're me. And so if you do nothing and you do nothing again, you'll just stay in the A position. So that's what goes in 0 times 0. So now, if you do nothing and then do a rotation, then you land in the B position, right? So now we start again in the A position. If you do nothing and then flip over, you get to C. And now start again in the A position. If you do nothing and then flop, you get D. Okay, that's all very well. Now down this column, it's going to be the same thing, because going down this column says, do the thing and then do nothing. And that's fine, because with this particular thing, you can do nothing anytime you want, and it doesn't matter. Sometimes it does matter when you do nothing, like as I said in my talk earlier this week, if you're making souffle, you don't want to do nothing for too long after making your souffle. But with flipping a mattress, it doesn't matter. So we'll get the same thing down here. So now let's try something a bit more exciting. Let's try doing a rotation followed by a rotation. So we start in the A position, we do a rotation, and then we do another rotation. So we get A. Very good. So let's keep going down this diagonal. Let's do a flip and then another flip. So we do a flip and another flip. We get A. And how about a flop followed by a flop? So we start in the A position again, do a flop, and we do another flop, and we get A. Right, so we get A's all down the diagonal. And what this tells us is that if we keep doing the same move all year, we'll just keep getting back to where we started and never hit all the other spots. And this is quite a profound result in mathematics. It shows you can't generate this entire situation by one single move. So we have to mix them up a bit. So let's try this one here. Let's try doing a rotation and then a flip. So we do a rotation, start in the A position, do a rotation, and then a flip. We get D. And now we can start in the A position again and try a rotation and then a flop. A rotation. C. And let's try here. Let's try doing a flip and then a rotation. A flip D, and maybe you can start seeing the pattern. Here we'll do a flip, and then a flop. So the whole point of this is I now get to say flip flop. So we flip, flop, B. I gave this talk in Italy once about this, and someone translated my slides into Italian. I can't remember what they said for flip and flop, but it was amazing. So now maybe we can kind of spot the pattern and guess, because there's various ways we can see the pattern, but it's also a bit like a Sudoku type thing, where there's only one of each letter in each row and every column. So what do you think goes here? C. And what do you think goes there? B. Right, so math, spotting the patterns is a part of math, and that can help guide us towards what's really going on. Of course, because we're mathematicians, rather than people on the internet, we actually check that we got the right answer. But I'll just tell you for now that we did get the right answer, because the main question now is how many Battenberg cakes can you see in this diagram? I'll just let you think about that. So there's definitely, it's a bit pale, but there's definitely a couple that are the same here. And there's a couple that are the same here. There's one in the middle, but my favorite one is that the whole thing is a Battenberg cake, each of whose small cakes was already a Battenberg cake. So here's one I made. Here, I'll put the letters back in to show you how this corresponds. I call it the iterated Battenberg cake, because we've iterated the process of Battenbergification. And mathematicians love iterating things. In some ways, we're just like small children who, if you figure out to do something once, you just want to do it over and over and over again to see what happens. So the process of Battenbergification here is like painting by numbers. You have a grid, and you've got two spots. And so all you have to do is decide what goes in spot 1 and what goes in spot 2. So it could be yellow and pink. It could be chocolate and more chocolate, because I love chocolate. It could be a bunny and another kind of bunny. So now I'm Battenbergified bunny. Or it could be one kind of Battenberg cake and another kind of Battenberg cake. And so there's my iterated Battenberg cake. I will say, if you try and make this, you have to cut so much cake off your cake to make it fit. You end up with practically more off-cut cake than the cake, but then you just make a lot of friends by giving them bits of off-cut cake. This is, in math, this is something else that you see in an abstract algebra class maybe, because the process of Battenbergification is where you're doing something with a cyclic group of order 2, and when you make a Battenberg out of a Battenberg, you iterate it, you're taking the cyclic group of order 2 and you're taking the product of it with the other cyclic group of order 2. Then you can multiply any groups together. You can take the cake of any group and use the cake of the other group to make each individual little cake is then the cake of the other one, and that's how you make products of Cayley tables. And I only figured this out when I started thinking about Battenbergification. But anyway, here's another way you can represent the situation, because all we had to do was ask ourselves what was going in position 1 and position 2. So we could draw it just like this and say, well, what's going in 1 and 2? Is it yellow and pink? Is it light brown and dark brown? Is it bunny 1 and bunny 2? Or is it cake 1 and cake 2? But what is cake 1? Well, cake 1 was just one of those, and cake 2 was just one of these. So how about I put this whole diagram for cake 1 where it says 1, and I put the whole diagram for cake 2 where it says 2. And now I've made another kind of mathematical structure that I really like, which is a tree. It's called a tree because it looks a bit like a tree. It's an abstract tree. And the nice thing about abstract structures is that you can think of them in a lot of different ways. Trees usually grow from the bottom up, right? They don't usually start with leaves in the sky that somehow coalesce into roots. But because it's an abstract tree, we can read it either way. We can read it as something at the bottom made up of these things. But we can also read it from the top down and go, oh, we're going to start with these ingredients and make this thing. And that's how I like thinking about trees, which is from sticking things together. So for example, here is one way of sticking 3 things together, where I'm going to stick the left 2 things together first and then the right hand one afterwards. Whereas another way of sticking 3 things together is to stick the right hand 2 things together first and then add the left-hand one. So if these were numbers, we could ask if this was equal. For example, you could say 4 plus 4 and then 2 afterwards. And well, 4 plus 4 is 8, right? And then you add 2 and that's 10. But when we're stuck writing our algebra in a one-dimensional straight line, we have to use these annoying parentheses to indicate where we've done things. And I find that kind of annoying because I like the higher dimensional representation. So that's this one with the parentheses around the 4s. Over here, we would say, well, I'm going to add the 4 and the 2 together first and then add the 4 on afterwards. And it does make the same thing, but like this, we use the parentheses around here. You may remember this as the associative law for addition, but it's really about moving a branch of a tree across from left to right. And when it's numbers, these are equal, but when we're doing more subtle things in the kitchen, it might not be equal. For example, if we mix egg yolks and sugar together, and then we add cream and we heat it up, we get custard. Whereas if we mix sugar and cream together and then we mix egg yolks in and heat it up, well, we do not get custard. So these things are not equal. But if we're making cake, it turns out it doesn't really matter. The traditional recipe I grew up with says you cream the sugar and the butter together and then you add the eggs and then the flour and then you bake it and you get cake. But I have this theory that there's a big conspiracy by Big Cake who want you to buy cake mix. So they want you to be convinced that making cake is really hard and that you definitely need to buy their mix. But actually all you have to do is chuck everything in a bowl and go and it's going to be okay. It will. So it's not exactly the same, but what we've done is we've done a process of, we've been thinking about moving the branch from left to right, and we made 2 different ways of putting 3 ingredients together. So what are all the ways of putting 4 ingredients together for cake? Well, here they all are. And so here is the traditional recipe where you start with the sugar and the butter and then the eggs and the flour. This recipe says, I'm going to beat butter and eggs together first. That's quite strange. And then I'm going to add the sugar and then the flour. So this one also starts by beating butter and eggs together, and then you add the flour, which is also quite strange, and then you add the sugar. So this one starts entirely at the other end. You mix eggs and flour together, which is also quite bizarre, and then you add the butter and then the sugar. This one is pretty interesting because you need 2 bowls. Because you mix the sugar and the butter in one bowl, and you have to mix the eggs and the flour in another bowl, and then you mix the results together. And so then you might ask yourself whether all of these things are the same. And the thing is that it really depends, because in some of them, like in this one, your cake mix goes through a phase where it looks quite a lot like vomit. Maybe you don't want that. Now, if you're not doing the dishes, maybe you don't care that you made an extra dish dirty, but maybe you do care. So I did a talk at the Culinary Institute of America, and we did this with some of their chef students, and they made cake in all of these different ways in this amazing demonstration kitchen. And then we baked it, and we had a look, and they were all basically like cake. Some of them rose a bit more than others, but I quite liked dense cake. Also, it wasn't a terribly controlled experiment, honestly. But the thing is that in higher levels of math, you get to choose what really counts as the same or not. So maybe if you care about what your cake mix looks like in the middle, you don't want to do one of these ones. It's true that if you don't have an electric mixer, it's definitely, this one is definitely the easiest to do if you're doing it by hand with just a wooden spoon. But maybe you're not the one who's doing the cleaning or the baking, and then they're all going to come out more or less the same. And so what happens in higher math is we choose which things will count as the same or not. And this is actually a very important result, or a really important concept in my research in higher dimensional category theory. It is the McLean associativity pentagon, which I didn't meet until I was a grad student. But really, it's just about making cake in different ways. And the most obvious next question, math is all about being led to asking more questions by your curiosity. The obvious next question here clearly is, what if I want to make chocolate cake? Because clearly I do want to make chocolate cake, because everything is better with chocolate in it, maybe not fish. But maybe soy sauce is fantastic. And so if you make chocolate cake, you just have to add chocolate. Then you've got 5 ingredients. And so then you might want to draw all the possible 5-leaf trees. And then what you find is that they fit together in a bunch of different pentagons like this. And here is what shape you get, someone 3D printed this for me. It's called it's the 5 associahedron. And so then you can generalize it so that if you have 6 inputs, you get the 6 associahedron, which is then going to be a 4-dimensional shape, because with every extra leaf, you get another dimension. And a lot of my research is in figuring out how these things fit together with each other in higher dimensions, because it gets awfully complicated. And that's the thing, that these things do get complicated. It is much easier to just ignore the complication, but just like in life, there are plenty of people who just ignore the complicated details about the world that they don't feel like understanding. And that is one way to understand the world better, to simplify it by ignoring stuff. I think a better way to simplify the world is to become more intelligent, because then the world becomes simpler relative to your brain. And I think that's a more productive way to understand the world. And my favorite way to do it is in category theory. So I'll just finish by telling you very briefly what category theory is, which is, I think that category theory is the mathematics of mathematics. And if I say that mathematics is the logical study of how logical things work, then, well, if category theory is the mathematics of mathematics, if we substitute that in, then we get that category theory is the logical study of how logical things work, which may sound very looped up on itself. But as I've done more teaching to art students who are previously not at all interested in math, and more speaking to general audiences, what I've realized is that that abstraction helps me understand the world better at very deep levels. And it's a bit like the fact that if you're holding a flashlight and you shine it, raise it up higher, you eliminate a broader area, although you've lost a bit of the detail. And what you get is more of an overview, you see more things around where you are, and you get to connect more things to each other because you see how things are related to each other. Bless you. As I hope I've shown in this talk, many things can be related if you go into the world of math, and then you get to see connections between things that you didn't see before. And I do want to say that I think it's really important to remember, I'm not trying to say that we can use math to understand everything in the world. That's not what the point is. What I think is that the part of the world that behaves according to logic is a really important core part of the world. It's kind of the easy part in a way, and that what we should try and do is put as much as possible into it so that we can reserve other parts of our brain for the parts that are less easy than that. But for me, the parts I love the most are just on the interface between the things we can understand using logic and the things we can't quite understand using logic. To me, that's where the beautiful things are, like in a piece of music. I can analyze the mathematics in it all the way to a certain point, but then right at the end, there's going to be something else that I won't be able to explain that is exactly why it makes me cry, or why it makes me feel such deep, amazing emotions. And so for me, it's right on that boundary of logical things and not logical things that I think all the beautiful things are. And I have this image that the logical sphere of the world is this sphere in the middle of everything we understand. And as we put more things into it, the sphere grows. And as it grows, its surface grows. And because the surface is where the most beautiful things are, I think that putting more things in the logical sphere gives us more and more access to beautiful things. Thank you very much.